the title is Dependence on Initial Conditions and Couplings for the Chaos Synchronization Networks of Rulkov Neurons. So summary, first they present a model that is a network of maps, the isolated dynamics, how you couple the neurons, the maps to make the complex networks. So, and then the trajectories in the phase space. And how the individual dynamics is expected individual dynamics is chaotic. Then I explain, I show the results for a simple case of on a master, a Rulkov master, and a Rulkov slave, in which we exemplify the use of a simple quantifier for chaos synchronization. Then I discuss how there is dependence on initial conditions for the occurrence of chaos synchronization. Then there is somehow preliminary, but it's a very interesting result. There is a limited number of possible trajectories in the chaotic transient before chaos synchronization takes place. So I showed the results for the master-slave network system. That is, the slave system can suppress any perturbation. Also preliminary, there is multiple states in the transient dynamics. I can induce transitions in the multi-stable system among states, right? I show the transition between three states induced by monetary perturbations or for a small amplitude noise. Then I finish with my conclusions. So the Rulkov map is very simple. It has two variables, x and y. X is the fast variable. It simulates the membrane potential of a neuron, and y is a control variable that controls the burst field. In the model there is the linearity here, and in this linearity we have parameter alpha, that is the bifurcation parameter, because it controls how chaotic or how large is the maximum Lyapunov exponent of the model. So these are the time evolution of variable x and y. So you see, if alpha is small, the dynamics is almost periodic oscillation. And as it gets higher, there is chaotic spikes emerging there. So the dynamics becomes more chaotic. So this is the attractor for the model. It has this head with expected more occurrence in this long tail. So where the case period happens. So as I said, the individual dynamics is chaotic. So in this movie, I show that two almost identical initial conditions evolve in different trajectories, the blue and the red one. And the Lyapunov exponent for the closed system is positive, or almost positive. So chaos synchronization. Chaos synchronization is a strong case of synchronization for that said. That is, if you have a master forcing a slave with one initial condition, and you have other slave that is an auxiliary system that is identical to the first slave, but it has a different initial condition. It can be any initial condition. There is no limitation in that sense. The only limitation is that the same signal sent by the master to the slave must be sent to the auxiliary system. What you see if you have this right set of parameters where chaos synchronization occurs is that the Euclidean distance, or the difference, absolute value between the variables of the two systems, will have an exponential decay. So this is the completely opposite curve we would expect for a chaotic system, correct? That is an exponential decay. So this is chaos synchronization. Our quantifier is simply to measure the amount of time the two systems are, the difference between the auxiliary system and the real system, the slave system, is below some threshold, where we call that the trajectories becomes identical. So this is quantifier. Delta is the Euclidean distance between the system started at different initial conditions. If delta goes to 0, the trajectories becomes the same, and then the step function we start to mark 1. So if f is near 1, the chaos synchronization took place quick. If it near 0, it didn't occur, or if it is 0, it will probably never occur. All right. So for the simple system of one Rulkov and the other Rulkov, we showed that result that you write the maximum Lyapunov exponent, inverse the conditional Lyapunov exponent, that is the usual Lyapunov exponent, but with the condition that there is a signal imposed by a master to this slave. So we look just for the Lyapunov exponent into this slave, but for the maximum Lyapunov exponent, in the case it is not forced because it's autonomous, so you can use the usual Lyapunov exponent. If it's forced by the master, we cannot use the usual Lyapunov exponent. You have to use the conditional Lyapunov exponent. The conditional Lyapunov exponent is lesser, the maximum conditional Lyapunov exponent is lesser than 0 for this range of alphas. So in this region, you can say for sure that chaos synchronization occurs. The maximum Lyapunov maximum conditional Lyapunov exponent, if it's negative, at the same time the maximum Lyapunov is positive, it's an indicator that chaos synchronization occurs. However, there's a problem with the approach using Lyapunov exponents. That is in the critical region, where the error bars are big, and you have a high sensitivity to the parameter alpha. That is, you can vary alpha and the chaos synchronization occurs or not, and it's not easy to predict. It's not a monotonous curve. And other thing is that each dot is for a trial for a specific initial conditions. You see that they can spread in the y-axis. So there is a huge dependence on initial conditions for cave synchronization in this critical region. So this is the network of Rulkov maps, the system. It has an internal coupling that comes from connections from the network, and it has an external coupling that comes from the master network. So this is the contribution for the signal sent by the master. The master drives the slave. So here I show for a specific neural network how the perturbation can progress. So in the gray area time window, I applied some perturbations, strong perturbation, and each curve corresponds to a set of couplings. So you see that if you change the coupling, chaos coordination can occur rapidly. If we use the set that is in the blue, it can have a huge chaotic transient, or it can never occur in the black case. So also you can look at some parametric space. That is in the x-axis the internal coupling, the y-axis the external coupling, and you'll see that each network generator has its specific pattern in the parametric region. That is, it doesn't matter if you change one connection or the other. You just have to maintain the same algorithm to build the network. That is most important. So the network can be robust to perturbations, and it depends only on the method you use it, the law you used to make the connections, not from isolated connections. So it is robust if you destroy some connections or not. All right. So you also show that there are some strong convergence that chaos synchronization has almost no transient. That is because there are some conditional Lyapunov exponents there, their maximum Lyapunov exponents that are really negative. So these are responsible for quick convergence. All right, so these are the, I think, most interesting results. They're some kind preliminary, but you can generalize this methodology for a master, then several auxiliary systems of several slaves, you name it, that all the auxiliary system receives the same signal, and each auxiliary system has a different initial condition, and then we analyze what will be the trajectories. If after a transient, all the auxiliary systems will have the same trajectory, if they will not, and the result is that yes and not, because some auxiliary systems will have the trajectory conversion for one another first, and others not. So if you look in this case on the left, all the auxiliary system converge kind of at the same time for the same trajectory. But if you take a closer look on this on the right, it's very interesting because the uh, although they were initiated with different different initial conditions, the red curve converges to the blue curve first, then to the others curves. So the, there are some convergence to other one trajectory that's preferential than to other trajectories. At the end, all trajectories will converge to a master, a specific one, but while its transient is big, is large, there are several trajectories that the system can choose. And then you can count the number of trajectories that I will call states, because I will show that these trajectories are stable for some period of time in the transit, not if I have infinite time, but at finite time they exist. They are most stable, and they are robust to some small perturbations. So I show also that if you wait, uh, the more you wait to count, the lesser trajectories who you will observe. So you can induce transitions. That is, for example, here I have three auxiliary systems, and I have a fourth system that I use to analyze. In this fourth system, I add perturbations. So first, the analyzed systems falls into the blue state. Then I force it, and it falls out the blue and falls into to the black. Then it falls out the black, falls in the red, and then it returns to the blue. This shows that there are at least three states, and I can switch between these states using perturbations. If you use small amplitude perturbations, in which they are right specific amplitude, the transitions can be intermittent and can be spontaneous, and it's a very interesting result. Here I have two auxiliary system, and some noise can induce transitions between the two. After the transit, I also show that the two trajectories become the same where chaos synchronization took place. So as a conclusion, I show that dependence on couplings forces the network topology provide a background where brain plasticity can act as an agent of stability, which is the basis for learning and memory formation. The graph generator used to make the network is more relevant than different random connections to ascertain the couplings for which chaos synchronization occurs. We believe that further achievements have the potential to establish the method as an additional analysis tool for complex dynamical systems. Being able to examine the momentary dynamics of high-dimensional systems through the observation of states comparable to multi-stable ones. Thank you for your attention. Any questions? My contact is here, my email.